Welcome everybody, welcome to ClayDesk. My name is Syed and I am an IT enterprise architect and DevOps engineer, and I consult with enterprise companies all across the globe. So we are going to learn the characteristics of reactive systems, and I will also explain what are reactive systems, so not to worry. So if you're new to this channel, please subscribe and hit the like button and also the bell notification so you get notified every single time I upload the latest and full technology courses, right here on YouTube. You can also take our courses for free or navigate to claydesk.com and get unlimited access to all of our courses. All right, so let's dive right into reactive systems. We know that typically today architects, cloud engineers, developers are expected to implement highly scalable and resilient distributed systems on either AWS, GCP, or any other cloud platform. So microservice applications requirements have changed dramatically in recent years. And many modern applications are expected to handle petabytes of data, right? Require close to 100% uptime and deliver sub-second response time to users. So typical end-tier applications cannot deliver to these requirements, right? So today, reactive architectures and reactive systems have been adopted by a growing number of enterprises because it is necessary to design applications in a highly scalable and responsive manner. But what exactly is a reactive system? Let's talk about that. So organizations working in various domains are independently discovering patterns for building software that look the same. These systems are more robust, more resilient, more flexible, and of course better positioned to meet modern demands. So systems built are reactive systems are more flexible, loosely coupled, scalable, and this makes them easier to develop that can easily change. They're more fault tolerant to failure, and when failure does occur, they can cope up with it. So reactive systems are highly responsive, giving users effective interactive feedback. So let's take a look at now the characteristics of reactive systems, right? And this is really important because if you understand these systems, it'll definitely help. So first, responsive or responsiveness means that the system responds in a timely manner. It is certainly crucial to reduce latency between request and response. Latency is an important factor that can, under certain circumstances, by the way, be very, very decisive for the success and failure of a service. It directly influences the behavior of the consumer website or the web service itself. So imagine you want to check out your shopping cart on an e-commerce website, right? And then processing of the payment takes significant amount of time or even crashes. Not good. So this results in a bad user experience, right? So latency is often correlated with conversion rate. So responding in a timely manner definitely ensures that these systems deliver consistent behavior and quality of service. So the resilient systems also stay responsive in the face of failure. A resilient workload, by the way, has a capability to take heavy loads, and failure of any component on the workload components is critical. So if a failure occurs in one component, for example, this must be contained in the source and isolating from other failures. And this prevents from small failure causing a major outage of a complete system. So the reactive architecture remains responsive under varying workloads. And this elasticity, by the way, requires you to be able to scale dynamically and add or remove resources to react to changes, which leads to avoidance of bottlenecks. Now, these systems support predictive as well as reactive metrics, for example, that leads to efficient use of resources. Message driven, by the way, between boundaries and services, reactive systems rely on asynchronous message passing. Now, this helps ensure loose coupling, isolation, and then location transparency. Now, location transparency can be achieved by, let's say, using a message queue or a similar system without the explicit knowledge of the location. This can be achieved, by achieving network resources like DNS, the main advantage, by the way, of this approach is that it's not important where exactly the resources are located. And this is really key for resiliency and elasticity because a failover mechanism can be implemented that abstracts the actual resource behind the network name. So in reactive systems, asynchronous message passing is also used to distribute information of failures or other errors as messages. So by using this pattern, the system enables better load management, by monitoring the message queues and implementing a message, mechanism for back pressure. And this allows non-blocking communication, which leads to less systems overhead. One of the biggest challenges to effectively scale large systems is the bottleneck that is introduced by shared resources. Now, this communication pattern helps minimizing concurrent access. So what's the difference between message-driven and event-driven? Well, basically, for example, an event can be a change, for example, in an AWS environment. Let me give another example. Amazon EC2 auto-scaling generates events when it launches or terminates instances. So a message, however, has a clear direction. It's a command sent to a system. The destination reacts, by the way, on a message, that starts on an action. So let's talk about observability and tracing, right? So reactive systems are defined as message-driven and resilient, which means reactive systems by nature will be a distributed system. Now, this necessarily includes additional network communication, for example, in a traditional monolithic application, by the way. For example, a Java, application, a complete application, by the way, resides in the same memory on one device, potentially with 4 redundant copies on other machines to allow for failover. Now, in many cases, monolithic applications, right, have better latency compared to distributed applications, but with limitations in scalability and availability. So the example application that I'm going to talk about, by the way, give you an architecture that will explain to you what reactive systems are and how it works. So that architecture is coming in just a moment, right? So basically, what you're looking at when we talk about reactive systems is, due to the nature of these reactive systems, involves communication over network, for example, and across server boundaries. The additional latency has a huge impact on the performance of the overall application. So if there is an error in let's say in a monolithic application, for example, an exception was found in one of the log files, debugging the problem is often relatively easy due to non-distributed nature of the application. So a typical microservice, on the other hand, application that passes messages for communication is harder to debug because it is sometimes not possible to reproduce the exact state of the complete system and then replay the events in order to reproduce all these issues. So each service has a separate log file, even though those log files are often consolidated in a central system, such as Amazon CloudWatch logs or Amazon OpenSearch service. What are the typical use cases of reactive systems, right? So the essential characteristics of reactive systems, we already talked about those, right? So the use cases for reactive systems have in common, let's take a look at those. So potentially millions of messages flow into the backend system, right? The impact of this requirement, within this backend system is able to quickly scale out and is resilient. For example, advertising technology, ad tech, they face an interesting challenge to collect and track a lot of information. And typically this is, tracking pixel on a website, right, that ingests data into a system. Now, depending on the campaign and its success, the amount of data that needs to be collected and transformed may significantly vary and is not always predictable. So, I'm going to be talking about, an example implementation of these systems, and I'm going to talk about the architecture as well. So, for example, for e-commerce, it is a similar situation. If a product goes viral on social media, right, or an advertising campaign is surprisingly successful, a lot of people will visit that e-commerce website and order products. So for, let's say, IoT, as another example, you need to manage millions of devices that produce a huge amount of data. Now, this data needs to be collected, stored, and then, of course, analyzed later, right? So often it is necessary to send additional data back to the connected devices to update the status. So you can imagine the massive amount of data. And the complete system must be responsive to deliver feedback to users and trigger changes to the devices or all of these IoT machines within a span of time. Let's now take a look at an example of an architecture that I promised, how reactive principles can be applied to the real-world application, right? So let's dive into the architecture and just observe so that we get a clear understanding of not only what reactive systems are, but what the important characteristics that we just highlighted. So, to effectively take a look at reactive principles that can be applied to real-world application, this example architecture implements a reactive system, for example, for an ad tech use case, right? So many ad tracking companies, they collect large amounts of data, and I've already talked about that, right? So in many cases, these workloads are very, very spiky and heavily dependent on the success of the ad tech company's customers, right? They also need to be responsive and resilient, as these systems form part of the backbone of many ad tech companies. So in this particular architecture, in this example that you see, the system can be logically divided into one part that is focused on data collection and another part that focuses on core data updates. Now, the data collection subsystem is responsible for collecting, validating, and persisting the tracking data, potentially basically enriching it with some core data in the process. Now, in the core data update system, or the subsystem rather, the data that is used to validate and enrich the incoming raw tracking data, now this typically includes data on ad inventory, for example, campaigns, publishers, remaining campaign budgets, and so on. Now, they all receive updates from upstream back office systems and notifies all the subscribers about the changed and added data. Now, typically for an ad tracking use case, the data collection subsystem can be separated further, of course, into real-time part and non-real-time part. For the real-time part, it is important to collect data as quickly as possible. And of course, you can ask several questions such as, is this a valid combination of parameters? Another question could be, does this campaign exist? And of course, another question could be, is this campaign still valid? Now, because the response time has a huge impact on the conversion rate in advertising, and I highlighted this earlier too, it is important for advertisers to respond as quickly as possible. So any information required to decide on a response should be kept in memory to reduce communication overhead with the caching infrastructure. The tracking application, by the way, itself should be as lightweight as scalable as possible. So for example, the application shouldn't have any shared mutable state. So in this architecture, for example, that you see, one main application running in Amazon ECS is responsible for the real-time part, which collects and validates the data, responds to the client as fast as possible, and of course, asynchronously sends events to backend systems. The non-real-time part of the application that you see, by the way, consumes the generated events and persists them in a NoSQL database. So in a standard tracking implementation, this includes clicks, cookie information, or could be transactions. Once stored, they're later matched asynchronously and persisted in a data store. So in this example that you see right here, one more time, basically the request, which is the impression or clicked ad, is ingested to the application load balancer, which routes the incoming request to one of the service instances in the main application. And of course, the cache, which is stored in the memory of the application, stores the most recent core data updates. And of course, there's also an open connection with the L2 cache here. The application processes each incoming request separately. It's implemented in a responsive and resilient manner and doesn't write directly to a database. Rather, it uses Amazon Kinesis data streams. New events are added to the data stream and consumed by the AWS Lambda function, which simply writes the data into the Amazon DB or DynamoDB table. Now, the data stream implemented with Amazon Kinesis, by the way, acts as a main buffer to decouple the database from the application and ensures that this event data under load is not lost. Now, with this architecture, definitely you can reliably process a huge number of events and store them safely. All right, so I hope it makes sense. Now you understand what reactive systems are and, more importantly, the characteristics of reactive systems. And of course, we also took an in-depth look within the architecture and a use case. So I hope this makes sense. Let me know if you have any questions. Post your questions in the discussion area. And of course, do not forget to like, comment, subscribe, and of course, share, because ClayDesk is your #1 e-learning channel. My name is Syed. Thank you for watching, and I'll see you guys next time.